I'd like to thank everyone. Well, thanks to all the students for all your hard work this year. We've had such a blast getting to know all of you, and every week just working through all things related to research facilities, major facilities, cyber infrastructure, data life cycles. So thank you all for all your hard work, and it's going to be fun. Continue on as part of alumni, and also those of you that are moving on to projects for the summer. We are having our first two group presentations today. So group one is going to focus on NSO and group two will focus on GAGE. And so we'll start with group one. We'll go ahead and make sure that that will be Ejay, Macy, Aidan, and Emma. And you can share your screen and get started.
Hello, everyone. Thank you for coming to our presentation. We decided to do our overview on the NSO, which stands for the National Solar Observatory. I'm Aidan.
I'm Ejay.
I'm Macy.
And I'm Emma.
And let's just jump into it. So as for the mission of the NSO's main objective is to study both the sun as an astronomical instrument, so in space, and as it affects everything to do with the Earth, which in practice is involving itself in building various solar instrumentation in observatories and research institutes all around the world, which you can see here. There's quite a bit. There's 8 official sites with headquarters in Boulder, Colorado, as well as a major facility in Hawaii, though this number can vary depending on who you ask, mostly to do with its collaborations with Aura. Aura is the big head organization that the NSO operates under. It's a nonprofit with ties to, well, I should probably name it first. It's the Association of Universities for Research in Astronomy, which basically just means that it's a big figurehead that operates in all over the world. And the NSO has projects and contracts with a lot of different organizations, both through universities and through industry and government contracts.
So the NSO collects multiple forms of data to better understand how the sun works and how it affects the life on Earth. First, they collect magnetic field data using something called magnetograms, which shows the strength and direction of magnetic fields on the sun's surface. They also capture high-resolution solar imagery, which includes details like sunspots and plasma cells. If you could turn your attention to figure 1, it's what they call the famous honeycomb image, which was taken at 789 nanometers. Because of that boiling look, it caused a convection cells to rise and fall on the sun's surface, hence the honeycomb image. Then there's spectral data, which helps scientists identify the sun's chemical makeup by analyzing its light. And finally, helioseismic data, which tracks wave-like vibrations across the sun's surface to uncover what's happening in the inside of the sun. Next slide, please. To gather this many data, NSO uses some serious, impressive instruments and quite a few. At the center is Daniel K. Inouye Solar Telescope, or DISC. It's the largest telescope in the world, which is based in Hawaii, and it stands at 12. Its massive 12-foot mirror lets it gather more light and resolve finer details than any solar telescope before it. Light collected from the sun is guided through the telescope and sent down into a large rotating table where it has 5 major instruments. 4 of them are the spectral and polarimetrical instrument, and the other one is a high-resolution imaging system. The spectral instruments break down the sunlight into individual wavelengths, kind of like splitting a rainbow. Each element, like hydrogen, helium, or iron, absorbs and emits light at specific wavelengths. So by analyzing these wavelengths, which are present or missing, scientists can figure out what exactly the sun is made of. The polarimetric instruments take things a step further. They measure the polarization of light, basically the direction that light waves are vibrating. And this is important because polarization reveals information about the sun's magnetic field, its strength and direction. The really cool thing about this, about disk, they measure the polarization of light, basically the direction. Oh, I'm sorry. Because the Earth is rotating, the sun appears to move across the sky throughout the day. If you were to keep the instrument still, the movement would distort the incoming data. So because it's on a rotating table 2 stories below the main telescope, this table slowly rotates in the opposite direction of the Earth's rotation, which allows the instruments to track down the sun in a stable fixed frame. This setup makes sure that the light, excuse me, make sure that the light entering each instrument stays aligned throughout the day, even as the Earth moves. That way, all the spectral and polarimetrical measurements stay accurate and consistent, which is critical for long-term solar research. NSF also operates other projects like SOLAS and GONG to capture long-term solar trends, and they collaborate with space missions like Solar Orbiter and Parker Solar Probe to observe the sun from different angles at the same time. And that's what you call a multi-messenger astronomy. Next slide, please. After the data is collected, it gets processed through NSO's data center. One of the first and most essential steps is calibration. This step removes all distortions introduced by the Earth's atmospheres, mirrors, or even the cameras themselves. In that way, the final image is a scientifically accurate representation of what the sun would look like. On the right, I just put a simple flowchart to help showcase this process visually. This chart wasn't from the NSO website, so while it gives a good overview, it may not be perfectly accurate. So it starts with calibration, and this part is still after calibration, image processing is still in development, but the plan to use algorithms to detect features like sunspots automatically, they would have to collect the features across time and help track solar activity more efficiently. And then with calibration, it starts with raw data acquisition, where it basically takes the telescope to capture sunlight with its instruments. And because it's raw data, it doesn't really look, it isn't what the sun really looks like. There's full distortions from the atmosphere, noise from the electronics, and quirks from the telescope mirrors, as well as the cameras. And next, they would go through a dark frame subtraction, which removes background electrical noise, and then a flat field correction, which helps even out the differences in the pixel sensitivity and lighting across the image. Then they would do an optical distortion removal, which corrects any warping caused by the mirrors and lenses. And once the data is calibrated and accurate, it goes to image processing, which I just mentioned earlier that it's still in development, but it is mostly of a future plan. And this part involves noise filtering, feature detection, and even automatic segmentation and classification of things like sunspots and flares. Next slide, please. And the next 2 processes are spectral analysis and helioseismic analysis. Spectral analysis is my personal favorite. That is where they split the light from the sun into different colors or wavelengths, like a rainbow. If a certain wavelength is missing, that tells us what the element, like hydrogen or helium, absorbed it. Every element has its own spectral fingerprint, so this method helps scientists figure out what the sun is made of. Helioseismic analysis is like listening to the sun. Vibrations ripple across the surface and pass through the inside, just like how on Earth we have earthquakes. By studying how these waves changes, scientists can estimate the density and structure of the sun's interior. And going again on the flowchart, I just made it personally and tried to make a visual. On the left side, we have spectral analysis. This is where the telescope breaks sunlight into component wavelengths. Some wavelengths appear very strong, while others are completely missing. And that missing light tells scientists which elements are in the sun. The steps include calibrating the spectral lines, which removes the background and compares them to known spectral fingerprints from the lab test, just so we know what material the sun has absorbed. And on the right side, we have helioseismic analysis, where the sun actually vibrates or quakes, ripples across and even through the sun. And they track these wavelengths and measure how long the waves take to travel and how they alter. Scientists can infer what the sun would look like in the inside. And this is really important because we can't really see it in any other way.
Okay, then for data archiving and preservation, the NSO has a historical archive that's an online repository of major NSO data sets. But there are some data centers and archives specific for individual telescopes and projects. For example, the DISC data archive, which I took a screenshot of on the right to just provide a visual. This data center maintains this telescope's data throughout its life cycle. Next slide. And then since the NSO is such a large facility, there's a long list of software that they use. I just provided a short list of some of the open source software. So first they use like Python, which is mostly used for coding, Globus for data movement, Ceph for science data storage, Postgres DB for search support, Airflow for pipeline execution management, and RabbitMQ for messaging. Next slide. And then a big issue for these major facilities is long-term preservation. The NSO has a data backup in AWS, but since the NSO handles large projects, they struggle with, once a project is complete, how to maintain that data after it's no longer being funded. And this creates a large problem for them to maintain that data. And the solutions are slightly varying, and no one is totally content and happy with the way it's being done. They're still trying to find out better ways to do that. And then for data dissemination, the NSO data sets are often made public. And there's also some additional raw data that is accessible upon request. They mainly disseminate their data to researchers and educators, but with publicly accessible data sets, anyone with like the necessary tools and software can access them.
All right, so another major aspect of the data lifecycle is data movement. So because NSO has so many facilities around the world, 8 facilities, the data needs to be transported a long way from the place that it's collected to the place where it needs to be processed. So for example, the DKIS telescope in Hawaii, the data needs to be sent all the way to the headquarters in Colorado before it can be processed. That's one major challenge that the NSO has. And another major challenge, like Macy said, is the legacy data. At this point, they are running out of physical space of places to actually store the data. So not just hard drive space, but like space in a server room or a warehouse where they can actually place this data. So those are some of the major challenges of the NSO. And then for future plans, because the DKIS telescope is fairly new, it began operations about 3 years ago. There's a lot of ongoing research into the magnetic environment of the sun that they'll be continuing to do. And then the Global Oscillation Network Group, the current series of facilities known as GONG, those facilities are aging a little bit, so they're getting to be around 20 years old. So there are proposals in the works to build the next generation of the Global Oscillation Network Group, and these new facilities could be used to analyze exospace weather in addition to the sun, which can help us learn more about the potential habitability of other planets. And with that, here are our resources. And finally, we'd like to extend our heartfelt gratitude to Robert Tawa and Fraser Watson, who took the time to sit down with us and talk to us and share a lot of great information about their time working at NSO. And finally, we'd like to extend our sincere gratitude to the National Science Foundation for their generous support of this research project. Any questions?
Again, I'm just thanking everyone who was able to make it here today. We really appreciate you being here. And thanks to the first group for a fantastic presentation. It really seems like you enjoyed speaking with those at NSO and learning about NSO. So for our second group, we have the focuses on GAGE, and we have Spoorthi, Catherine, Elikem, and Dylan who will be focusing on that. So group 2, as soon as you're ready to go, feel free to share your screen.
Hi everyone, we focused on GAGE, which is the geodetic facility for advancement in geoscience, and the group mates were me, Spoorthi,
I'm Catherine.
and
I'm Elikem.
I'm Dylan.
did everybody go? Okay, next slide please. So the mission of the GAGE is The mission of GAGE is to advance the understanding of the Earth's dynamic system by providing the data and the tools and the infrastructure for it. Is my volume better now? I'm sorry.
You should speak louder because you're in a public space. So you speak louder.
Okay. So as I was saying, they utilize cutting-edge technologies such as GNSS and NSAR to monitor the Earth's surface and the environmental changes within it. Next slide, please. So some of the core values or some of the things that they've been working on for a while is enhance the understanding of crustal deformation and earthquake cycles, and then also volcanic activities and hazards related to that, and also measuring in water and ice sheets in the colder regions. So some of the methods that they use, as I mentioned, was the GNSS, which is a high precision surface deformation monitoring. And then they also use NSAR, which is the satellite radar. And then they use data services, which we will go into later. And then global partnership with multiple global tech companies and partnerships. So the GAGE is under like an umbrella called the UNAVCO, and this includes GAGE and SAGE, which are kind of like twin facilities, and it's the main headquarters is located in Boulder, Colorado, but they have thousands of stations across North and Central America, and they also have a very global outreach with networks all around the world.
So going off of sort of the structure that Spoorthi was mentioning, this is what's called the NODA network, is what you see on the screen. It stands for the Network of the Americas, and as you can see, there are stations all across North America, but there's even a couple of stations in Europe and around the world. This is overseen completely by the GAGE major facility itself. There are very many stations, as is seen by the very, very dense map. There's about 1,225 stations with more than 1,200 instruments total across the stations. With this, I'd like to mention that GAGE isn't necessarily centralized. So there are stations across the world. There are staff across North America. And there are also other networks besides NOTA that Earthscope and GAGE operate. It's just NOTA is the primary one that is operated. And the GAGE major facility was initially called UNAVCO, but they merged with Earthscope. So a little bit about the instrumentation and data capture that the GAGE major facility uses. As Spoorthi was mentioning, there are a few different data types. There's the GPS and GNSS data, which is the primary data that's collected with GAGE. But it's also important to note that GAGE assists in archiving synthetic aperture radar data, LiDAR and SFM data, strain and seismic data, and also tropospheric data. Some of these data are collected and managed by a consortium that's not affiliated with GAGE called WinSAR, but then GAGE archives this data for them. A few of the instruments that GAGE uses to collect their data include borehole strain meters. These borehole strain meters measure small shifts in the diameter and volume of the borehole that's placed underground. So in this center image here, there is a gray sort of area within the image. That's the tube that they would insert underground. The tube would be inserted about 100 to 250 meters underground to garner these very precise measurements. For example, a fun fact that I learned on GAGE's website is that they mentioned measuring a precision that's about 1/10,000,000th the width of a lock of hair. So very, very, very precise measurements. There's also a certain type of different strain meters, which are called Gladwin tensor strain meters, which from my understanding measure electricity levels as well as the diameter and volume of change of the strain meter. Borehole strain meters are only a small part of what can be included within the instrument. Instruments can also contain seismometers, tilt meters, and other data collection options. But these can also be individual. So not every instrument has to have the same the same ways to capture data. Seismometers also use sensors rather than track the diameter and volume, which helps detect small seismic events that occur underground, so something that maybe might not be detectable at surface level. Now going into the GPS and GNSS data, which GPS stands for a global positioning system, and GNSS stands for what's called a global navigation satellite system. These use receivers, which are shown on the top right of the screen, satellites and antennas, which are shown on the bottom right of the screen, to guarantee different types of accuracy. At least 4 of these instruments must be used in order to take measurements at different angles to ensure that precision. Now, raw data from GPS might only be based on one GPS, but post-processing might analyze the data from a lot of different stations, instruments, and even satellites from the same instrument, so accuracy and precision can be obtained. There can also be permanent and temporary stations, so there can be GPSs at a station that are meant to be mobile, that are meant to be used at a lot of different stations that can capture short-term data, whereas there are also some GPS systems that are meant to capture more of a series of events. Now shifting on to the data workflows, the left side is sort of my interpretation of what I've learned, and then the right side was gained from the GAGE website. So to start, from my understanding, data first flows from each instrument to what's called the ingress system, which you can see in the middle, via different transfer protocols. And even within the same station, one instrument might use a different transfer protocol than another. It really depends on the station and the project that's there. It's also important to note that data flow is not bidirectional. So data flows in the direction of the arrows that you see, minus the cataloging and query, which we'll mention later. And even with the different data transfer protocols, data can flow between the instrument and the ingress system at a 1-minute sample rate. The ingress system also initiates connections between stations and fields. There's a firewall that only the stations and ingress systems are able to access in order to complete data transfer. Then the data flows from the ingress system to the holding pond. This is still completely raw data. It flows in small chunks called packages, which are individually sent to the holding pond so that not all of the data is overwhelming the holding pond. Then in the holding pond, these packages are combined into larger groups of data. So the individual packages might be for a smaller time interval, maybe 1 minute, whereas in the holding pond, the data might be combined to complete a full day, an hour, whatever the project requires. And the individual chunks all have the same time interval at which they come to the holding pond. So if the time interval is 1 minute, then all of those packages are going to have data that is 1 minute. But the data that goes to the holding pond might be a collective larger time frame. Then after the data comes to the holding pond, it's processed by cleaning. So this is level 1 data because now it's processed. And this data cleaning could include removing duplicate packages because some packages could accidentally be sent twice or multiple times. Then after the data is cleaned, it's then archived, which my group member Dylan will speak more about. And then you see the catalog here in this triangular formation. This provides insight into how the archive is actually organized. So users can access the catalog via a query to request information, and then they receive this information. Then data can be disseminated directly from the data holding pond to the user. So there's 2 ways that the user can gain the data. And now I'll pass it off to Dylan.
Awesome. Hi, y'all. So I'll be talking mainly about archival and dissemination. And so Catherine already mentioned that there's like a big ingress point. And so really what's happening at EarthScope is there's 5 kind of key considerations that they're trying to do, which is basically transitioning to cloud-based platforms. So we'll just kind of go through the 5 key focus points. First is just migrating data archives. So they're trying to transition all that GAGE and SAGE facilities to cloud and retiring any of the outdated physical hardware. And so that's kind of like where they're at in process. A big part of that is then user authentication, implementing access controls that will align with the NSF's security guidelines. So ensuring that everything's kind of secure and tight. The center one is optimization. So all these core facilities, as we all know, generate tons and tons of data. So they're trying to find ways to enhance computational efficiency so that you can then leverage cloud computing scalability so you can process them. One thing that GAGE is doing is introducing what they're titling GeoLab. It's going to be a Jupyter Hub-based platform, so you can bring in Jupyter notebooks and perform different data analysis pipelines. Key point for that is that you no longer have to go and get your data. It'll be accessed within that GeoLab. So because it's in the cloud, you can then work on scalability. And then finally, a big part of it, more towards the dissemination point, is engagement. So there's community engagement tools, so providing education, workshops, and documentation to kind of ease that transition from where they're at currently with physical hardware to like the cloud-based hardware. So we can go to the next slide. So this is kind of a figure actually when UNAVCO was still kind of leading GAGE, and it just kind of talks about like their processing of the cloud on-ramp. And so we're going to focus mainly on the 2 right columns, which is archiving and data distribution. And so essentially, right, data gets ingressed and processed, kind of how Catherine mentioned, and then we have to archive it. So they're all trying to implement it into different cloud-based services. So different types of databases, S3 storage. And essentially what happens is then it gets towards the distributed part where it could either go to the public, so you or I, we can access the data, download it if you didn't want to do the cloud platform, or once GeoLab's launched, you can access it there and kind of run all your different analysis pipelines. There's public Kafka. I think it's going to be an Apache, which is essentially live data stream. So you can get data as it's coming in from the instrumentation. So then you can do different monitoring type stuff or other types of analyses from there. And then finally, like EarthScope has its own private access internally. And so it kind of, it's unidirectional, like Catherine mentioned, but some of the data can be sent back to central processing and it can get reprocessed as archival data if it needed to be. And then this is kind of where they're at currently with this kind of like on-ramp construction for their cloud services. So just starting at the top, the data systems, I mean, they're just in process of actually bringing that archive data into the cloud and then ensuring that the workflows that exist are kind of like preserved. In the center, we see that they're kind of starting to kickstart that GeoLab Jupyter Hub. So in general, they're starting to implement it and test it and run some of these pilot services so that you can test whether or not the Jupyter system works for all the data. And then finally, we're like looking at the training and documentation. So it's just kind of like introducing the initial like wording and verbiage to go out into the public on how to use these different cloud-based systems. And like some stuff that they have coming up is like a big workshop in May where they're going to be introducing like how to use Cloud 101 services for GAGE and SAGE data.
So at GAGE, we all know that they operate a lot of GNSS stations, which helps them continuously monitor a lot of the Earth's movements. And in order to process and analyze this data, they utilize a lot of specialized tools. So I'm naming four of them. One of them is TEC, which stands for Translation, Editing, and Quality Checking. GAGE utilized TEC to ensure the integrity and the quality of raw GNS data collected from various stations. And they also convert this data convert raw data into certain formats to standardize the RINEX format by performing a lot of quality checks. Another tool that they use is the Gamut or GLOBE, which helps them analyze a lot of the GNS measurements to study a lot of crustal deformations and also estimating station coordinates and velocities. They use GIPS and OASIS to provide precise point positioning for applications and like monitoring tectonic plate movements and certain objects. And then lastly, they also use GPS velocity viewer to visualize geodesic plates, velocities, and also aiding into interpreting tectonic motions. Next slide, please. And so the challenges of data movement. So one of the challenges is that they handle a vast majority of data daily for specific challenges, right? They transfer a lot of terabytes of information, especially from remote locations. It's like almost like pushing a ocean through a garden hose. So for real-time application, even minor delays can be very critical. And integrating diverse data types from various instruments adds another layer of that complexity, much like assembling like a puzzle with pieces from different sets. So as the data collection grows, scaling the infrastructure can maintain performance and accessibility remains GAGE's top priority. Next slide.
This is the end of our presentation. We'd like to thank Tim Ronan at Earthscope for his expertise on GAGE's workflows. We were able to talk with him and understand more of the process for which data flows from place to place.
So thanks again, everyone, for being here. And also thank you to the students for a wonderful semester. We've really enjoyed having all of you with us, and we look forward to seeing all your hard work. And we always say once a CICFer, always a CICFer. So always make sure to reach out to us even after the spring. If there's anything that you need from us, we're happy to chat. But anyway, just thank everyone for being here. We're going to have our last two groups today. We have group number 3 that is going to be presenting on NEON, and group number 4 that's going to be presenting on NCAR. And so we'll start with group number 3, and that's Baydan, Tamara, Naomi, and Joanna.
All right. Hi, everybody. So we're going to be presenting on the National Ecological Observatory Network. So this is our team. So I'm Tamara.
I'm Baydan.
I'm Naomi.
I'm Joanna.
Okay, so we're going to start with NEON's history. So as you can see, NEON has been a long time in the making. So in 2000, the idea of NEON was conceived. Afterwards, the initial plans for the observatory were formed in 2006. From there, the plans were revised and edited many times before official funding was generously received from the NSF, the National Science Board and Congress in 2011. And then from there, construction began and was completed in early 2019. And then NEON became fully operational in the summer of 2019. So all the time and dedication and effort put into forming NEON, despite setbacks and uncertainty, really shows the need for NEON and shows the people who formed NEON really believed in its mission and purpose. Which brings me to my next slide. So what is NEON's mission? So per their mission statement, NEON strives to provide free and open data samples and infrastructure to enable the science of others. So what does this mean? This means in a technical sense that NEON strives to establish a comprehensive observatory network that's capable of addressing questions with real global significance. But this also means that NEON strives to, by providing this open access to a wide range of high quality data, to encourage the science of others that will allow us to better understand how US ecosystems are changing and how to manage our greater ecosystem more sustainably and to protect it.
So getting into a little bit of NEON structure, NEON is managed under the National Science Foundation within the Directorate of Biological Sciences. NEON operates under Battelle Memorial Institute. This is done under a cooperative agreement with the NSF. NEON overall is structured into 20 ecoclimatic domains, totaling to 81 active sites across the United States. They have a variety of collaboration and partnerships. NEON maintains a range of data partnerships with other organizations. These collaborations aim to enhance data discoverability, accessibility, and data accessibility. The partnerships include data partners, community engagement partners, data collection partners, and overall educational outreach partners. And overall, NEON utilizes their partnerships to produce usable and valuable data to support research, education, and environmental monitoring.
So like Baydan had mentioned, there's 81 field sites and they range across 20 different domains. 34 of the field sites are freshwater and then 47 are terrestrial. And for each of the domains, there's a domain site facility. So the domain site facility usually has a domain manager, and then there's a whole bunch of field crew that also work for that facility. And the field crew can be ecologists or technicians, but they'll work on the field year round, either with the actual sampling instruments or collecting samples. And NEON has a very complex sampling design. The goal of this design is to answer questions about global ecological change by taking individual local measurements. So for example, they situate a lot of their terrestrial field sites close to their aquatic field sites so that they can make connections about these different type of ecosystems and how they interact by just taking local individual measurements at each site. NEON collects data in a bunch of different ways. Some of it is observational sampling. This is done by the field crew for each domain. And then there's also automated instruments which collect data year round. And then there's the airborne remote sensing surveys, which are done every couple of years. Lastly, documentation is super important to NEON. They have very detailed and up-to-date documentation on all of their data processing methods, on their sampling methods, and things like that, and they're all available online to the public.
So just like Naomi said, NEON collects ecological data from across the United States using different methods. They combine automated sensors, field sampling, and remote sensing to make sure that the data stays consistent and comparable across different sites and over time. NEON tracks both atmospheric data and hydrological data at their sites. So for the atmospheric data, they use MIS, which is a meteorological instrumentation systems on flux towers, and they measure things like temperature, humidity, wind speed, and greenhouse gases. They also collect hydrological data in which they use the AIS system, which monitors the stream flow, water quality, and groundwater levels, which gives insights into the aquatic ecosystem's health. Another key focus is biodiversity. So they collect data through botanical surveys, like small mammal trapping, invertebrate sampling, and even microbial DNA sequencing. On a larger scale, they use airborne observation platforms. which carry tools like LiDAR, high-res cameras, which map ecosystems from above. And this combination of collecting data on the ground and aerial data helps link small-scale changes to bigger environmental patterns. Some examples of raw data that NEON collects include direct organism counts, specimen samples, and genetic material. So for instance, researchers track the number of birds, plants, and small mammals at each site. They also collect insects and fish through trapping and netting. Plus, they gather environmental DNA from soil, water, and to identify species at the genetic level. After collection, NEON data goes through a few stages of processing. So first, they have basic field level checks, which catches errors and records the metadata. And then they have more complex analysis like DNA sequencing and remote sensing, which are handled in specialized labs. They also use automated data pipelines to clean and standardize everything before it's made available to the public. So we could also ask ourselves, how do they keep the data current? They keep it current by uploading it in real time. They also regularly recalibrate their sensors and run quality control checks to make sure that the data stays accurate. All the data is then shared through NEON's open access platform, which I read that they also use the Google Cloud platform, so that scientists, educators, and policymakers can use it for their work.
The NEON data archival architecture is built on the Google Cloud platform, like Joanna had mentioned. And this platform has object storage capabilities to archive almost all of their data. They just don't usually archive data from the airborne remote sensing, and then they don't include multiple versions of historical data sets. This is just because both of these include very large amounts of data that they don't necessarily have the funding to store. But besides that, they try to keep a copy of almost everything within the Google Cloud. The other really nice thing about the Google Cloud platform is the tools that it has available. So some of those that they use are the Cloud Shell and Cloud Run functions, and these allow the data to be processed and reformatted all within the cloud. So researchers or people from NEON don't have to download data, reformat it, and then re-upload it to the cloud. It's all done in one place, which makes everything much more efficient and much more cost efficient. However, some of the challenges that they currently faced with data storage could be the cost. Right now, it's about $17,000 a month for their cloud storage, and this is relatively cheap for NEON. However, since NEON's a 30-year program, this cost is definitely going to increase, and it's hard to predict exactly how it's going to increase. So this is going to be an ongoing discussion and challenge as they move forward. NEON also disseminates data in a couple of different ways. First, they have the biorepository data portal. So this data portal has a lot of information about samples and sample availability, and it's linked to their physical biocollections, which is housed in Tempe, Arizona at ASU. This picture shows an example of some of the samples that are kept in the biocollections. So here on this data portal, people can find more information about samples. They can loan out samples. They can also store, external researchers can store their samples here. And the cost will just depend on how many samples they have and how long they need to store them. So that's the main purpose of the biorepository data portal. There's also the NEON data portal. This is more general and it's online, it's web-based, and it's very user-friendly. So it's really meant for anyone to just search through the different types of data they have available and find something that might interest them or what they're looking for. And then they also have the NEON Data API. So this is more programmatic, and it allows people to find and query for any specific data that they might be interested in finding. It also has a lot of metadata available. So that's information about the samples, information about all of the different sites, and information about the 150,000 locations. So while there's 81 sites, there's many different locations at a single site because there's so many instruments actually collecting data at the site. So it has very specific information on all of those locations. The GraphQL API is used for querying data, so researchers can find only the specific data that they might be looking for. And then NEON Utilities is an R package that NEON lets anybody from the public download. And it allows people to easily transform their data from a format that Neon provides to formats that are commonly used in data analysis. Another really nice thing that Neon offers is since they're within the Google Cloud platform, they have Google's tools available. So some of those include Google Earth Engine, BigQuery, Vertex AI, RadLab, or Looker. These are different tools that allow anybody to visualize the data, to query for data, to create Jupyter notebooks, to analyze data, to use AI, to kind of make conclusions from data, a whole bunch of different things. And lastly, Neon's main goal is to disseminate their data to anybody who might want it. So that could be scientists or researchers, it could be the public or the government, or it could be students or educators. So their main goal, which I think is really cool, is open and equal access of data to everybody. And they don't only have this goal, they really push for it to be achieved by offering a lot of different resources and services. So they have support services and workshops to show people how to work with their data, how to download it easily and draw their own conclusions from it. And then they have a really large document library with a whole bunch of different information on how not only they process their data and collect their samples, but also how you can use it, change it, analyze it, things like that.
So in terms of software, Neon uses a few different things. Some things that I wanted to highlight was Fulcrum. The Fulcrum platform is used for data entry in the field and at Neon sites, and serves as this kind of application for entering data for various protocols. Second, there's Symbiota. Symbiota powers Neon's biorepository sample portal, as well as the Neon public data portal that Naomi mentioned in the last slide. And those are just platforms that enable users to sample data, contribute, and learn about Neon samples. Most data analysis is done with Python and R, and Neon utilizes cloud for storage. As Naomi and Joanna talked about before, connectivity from sites goes back to the cloud, and then processing happens on Google's servers. And then in terms of hardware, Neon is pretty special in the sense because they use a mix of custom-made and then pre-made hardware. So first, for their instrumentation systems, they're primarily Neon uses like a mix of custom and things that are already made. So overall, their instrumentation systems are used to measure environmental variables in the environment. These things include things like flux towers, which is, I think, the first picture on there, climate towers, airborne sensing, and more. And the devices just measure a range of information about existing ecosystems. And then next, there's the data loggers. Neon primarily uses the GRAPE, which is grounded remote analog preferable equipment data logger. It's a custom designed device built specifically for environmental monitoring. GRAPE is responsible for collecting, storing, and transmitting data from a variety of sensors deployed across the field sites, including atmospheric, soil, and biological monitoring. Its design allows for remote management. So if there's some type of error or trouble in the network, they can fix it from miles away, and it's very reliable. So if something goes down, it can store copies of the data being collected. And yeah, it really fixes the issue of network and connectivity in remote locations. And then they have a location controller at each site. And this kind of just controls the entire system at the site, making sure everything is running. And then for challenges for data movement, from my research, there seems to be really two main aspects of Neon data that creates problems, that being the volume and diversity. As what's been said before, Neon has 81 sites in various different domains, and they're collecting various different types of data. So overall, a lot of different patterns kind of arise, but some main things that we can target is one, data volume. Some sites could produce over 1 megabit of information per second. And then with more and more things and instruments being deployed, this can increase as much as tenfold. And then in terms of diversity, they're collecting various types of data. So this data may need to be processed in different ways. So that kind of leads to the problem of data needing to be stored and sent. And then there's the issue with connectivity and bandwidth. A lot of the data is coming from these remote and rural areas with like limited network infrastructure. So they kind of had to make their own things to make sure that data is being sent on time back to the sites or back to the servers to be analyzed. Overall, the sheer volume and variety of data makes data management and storage and movement pretty complex.
Okay, so then lastly, we want to talk about NEON's future plans. So earlier this year, NEON unveiled their new 5-year strategic plan with goals including increasing partnership and collaboration, making data more readily available, and harnessing evolving technology. As NEON's only 6 years old, their cyber infrastructure is not exactly what needs updating, but rather in line with their goal of making data as accessible as possible, NEON hopes to incorporate systems like Apache Parquet, Apache Arrow, DuckDB, and similar data management systems. So many people use these systems to handle and manage their data efficiently, including researchers, government agencies, private agencies, educators, and students. So this really helps, incorporating these systems really helps to ensure that whatever their varied needs are, everyone has a way to access and utilize the data that NEON offers. Because at the end of the day, NEON wants to support everyone working to conduct important and relevant science. So then lastly, we'd like to thank everybody who helped in the making of this presentation, including the CICF team and our contacts at NEON, namely Dr. Dawn Lenz, Dr. Christine Laney, and Steve Jacobs. And we would also like to extend our gratitude to the NSF who generously funded this project.
All right, thanks so much, group 3. That was fantastic. I'd like to open the floor for questions. So now we have our last group, group 4, it's focusing on NCAR. And in that group, we have Jazzy, Priscilla, Nora, Entourage, and Rishi. And again, just wanted to thank everyone for being here again. We really appreciate all of the visitors that are coming in from, outside of CI Compass, and really the fellows, you all have done a fantastic job. So great work, everyone. Gonna go ahead and let group 4 take it over.
Hello, thanks for coming to listen to us. So we will be talking about NCAR, the National Center for Atmospheric Research. And just to hurry and introduce our team, we have Priscilla, Nora, Rishi, and Shori and Jasmine. So NCAR was first founded in 1960, so it's been operating for quite a long time, about 65 years now. It's based in Boulder, Colorado, and it was originally established by the National Science Foundation and is managed by UCAR, which is the University Corporation for Atmospheric Research, which UCAR's main goal is to support the university community by providing top-tier facilities and services for research in Earth system science. And the mission that NCAR really focuses on main key goals. First, it aims to understand how the atmosphere behaves along with Earth and geospace systems. It also works to support and expand what universities and the broader science community can do, both in the US and around the world. It also helps to share knowledge and technology in ways that improve life here on Earth and in the terms of science.
So NCAR really organizes its work into 5 key categories, and each of them tackles a piece of the Earth system that puzzle with the world's real world impact. First, we have weather, where scientists at NCAR are involved in each aspect of the weather science to create sophisticated models and provide the foundation to improve operational forecasts for the weathers. Then we have a focus in water, where the NCAR's goal is to enhance the water resource management and improve tools for like forecasting stream flow and flooding. Next up, we have climate. So this is about like understanding where our planet is headed to. And NCAR studies the impact of emitting greenhouse gas emissions, like global warming effects, and they're also quantifying the changes has made in the past and use that to predict the future of climate in our planet. Then we also have the air quality, where NCAR investigate in air quality from human health to crop yields and also provide forecasts and predictions. So, and finally, we have research on sun and space weather, where researchers working to understand the impact of sun that's more than 92 million miles away, and the chaotic magnetic fields. So scientists get better at forecasting the storm following events as they have more detailed understanding at the solar activities. So to support all these groundbreaking work, from tackling the weather patterns to modeling the future of climates and weather, and NCAR relies on some of the world's most powerful computing system. That's when these computing models comes in. As you see on the screen, their advanced computing models are engine behind the science, stimulate complex Earth systems with incredible details and accuracy. Some of the models have multiple versions, so they improve their accuracies and precisions over the new release. So these models allow researchers to analyze massive data sets, which we will talk about later, and runs experiments that will be impossible in real world and make predictions that help guide decision making across the globe. And next slide, please. So to power all these cutting edge computation, the CISC, which stands for Computational and Information System Lab, comes in to provide the backbone of NCAR's scientific work. Their mission is to support and advance the geosciences and with the technology and resources that researchers need to tackle big challenges about our planet. At the heart of the effort is Diracho, which is one of the most powerful supercomputer in the world. It is located at the NSF NCAR Wyoming Supercomputing Center, and it delivers a 19.87 petaflops of computing power, which is about 22 quadrillion calculations per second.
So NCAR's mission is to advance our understanding of the Earth system, but this wouldn't be possible without the collection of high quality data about the atmosphere, climate, and weather systems. So why is this data so important? Well, to think about it, our ability to predict hurricanes, track climate change, or to understand how the planet is warming depends entirely on the accuracy and the diversity of the data we collect. So NCAR combines cutting-edge instruments and methods to gather these data. So looking at the type of data NCAR collects, some of them are like grid data. So for grid data, you can imagine dividing Earth into a grid with thousands of squares. So grid data represents computed values like temperature, pressure, or wind at each grid point. So this type of data helps us model large-scale atmospheric patterns and trends. Another one is platform observation data. This is what we call in situ data, meaning it's collected directly from the source. Think of it like measuring temperature on site with a weather station or using remote sensors to record environmental conditions. It gives us a hands-on view of what's happening in real time. The cyclone-fix data is specifically used to track tropical storms like hurricanes by pinpointing a cyclone's location, analyzing its intensity, and projecting its path. NCAR can help provide early warnings and critical information for disaster preparedness as well. And with the model simulation data, this is where NCAR supercomputers shine. Scientists use this data to study climate and weather systems by tweaking variables like greenhouse gas levels or ocean temperatures. Model simulations help us predict future conditions as well, whether that's forecasting next week's storms or understanding how the climate might change in the next century. So each of these data types serve as a piece of a larger puzzle NCAR is working to solve. But how exactly does NCAR collect this data? So for chemical and atmospheric sampling, it uses pan-SIMS and atmospheric infrared sounder. So PAN-SIMS is a chemical ionization mass spectrometer, which is used to measure trace gases and chemical pollutants in the atmosphere. So this helps researchers understand the complex chemical reactions happening in the atmosphere itself. PAN stands for acetyl peroxynitrate in this instance, but it does measure other specific chemical compounds as well. With atmospheric infrared sounders, it processes climate data into detailed 3D maps. For example, it can create visualization of temperature or humidity across conditions that across different layers of the atmosphere as well. And for weather tracking and analysis, it uses C-band imaging radar. So this is mounted on NCAR aircraft and plays a critical role in tracking high-impact weather events like thunderstorm and tornadoes, and it helps scientists study the structure of these storms from above. In terms of balloon and aircraft-based observations, it uses dropsondes and radiosondes. So dropsondes are sensors dropped from aircraft into the atmosphere. So as they descend, they measure variable like temperature, pressure, and humidity at different altitudes. So it's like taking a vertical snapshot of the atmosphere. Radiosondes, on the other hand, are attached to helium balloons. And as the balloon rises, the instrument collects similar data as dropsondes and transmit it back to the ground. So this is especially useful for profiling the upper atmosphere as the balloon can go really high altitude. And for space-based systems, we have COSMIC 1 and COSMIC 2. So the COSMIC stands for Constellation Observing System for Meteorology and Ionosphere and Climate. So NCAR uses this to monitor atmospheric conditions across the globe, providing data that feeds into weather and climate models, which will be spoken more about by Priscilla.
So data is collected from various atmospheric instruments and they're transmitted and analyzed in many different ways. A key component of this topic involves the Global Navigation Satellite System, or GNSS, and this system refers to a constellation of satellites that broadcast signals for positioning, navigation, and timing. The most well-known GNSS system is the GPS, but NCAR goes beyond navigation and utilizes these signals for their atmospheric research by using a remote sensing technique called radio occultation, which tracks how these signals bend as they pass through the atmosphere due to changes in temperature, pressure, and humidity. By doing so, the NCAR scientists can create vertical profiles which measure how the atmospheric properties change at different heights. And an important project at NCAR that specializes in this technique is the COSMIC program, as Amsterdam has mentioned. And these satellites collect bent signals and convert them into valuable atmospheric data. And they're even able to do so in areas that traditional weather instruments can't reach, like in remote regions and even over oceans. This makes radio occultation a powerful technique for both weather forecasting and climate monitoring. And the image is from NCAR COSMICS 2 documentation, which shows how the satellites support global data collection through a network of downlink stations to receive the data and route it for processing. And through this global distribution, it helps ensure rapid access to data, which is essential for both weather prediction and space weather analysis. Continuing with data processing, COSMIC 1, also known as Formosat 3, was a collaborative project between Taiwan's National Space Program and the University Corporation for Atmospheric Research, or UCAR, and UCAR actually manages NCAR on behalf of NSF. Now, with the success of C1 launched in 2006, the United States agencies in Taiwan decided to move forward with another GNSS RO mission known as COSMIC 2, or Formosat 7. And through this mission, they launched 6 successful satellites a couple years ago in 2019. These satellites were more enhanced, having a higher sensitivity. They were able to compute a larger number of profiles per day and generate better vertical resolutions. And they were able to track both GPS and GLONASS signals. And GLONASS signals are similar to GPS. They just use a different system and frequencies, and they have a slight lower accuracy, but they're often just used as a backup in areas with poor GPS reception. And this was especially beneficial since C1 satellites only track GPS signals. And through these enhancements, this helped provide a revolutionary increase in the number of atmospheric and ionospheric observations. The images on this slide are from COSMIC documentation, and they explain how the satellites process data. In the top image, you can see the observational geometry of GNSS RO in action, where the GPS satellite transmits a signal and the signal bends as it passes through Earth's atmosphere. And as mentioned in the previous slide, this can change due to different components in the atmosphere. And this allows them to retrieve vertical profiles of the data collected. And from what I understand, the graph on the right side of the image visualizes these profiles, showing how properties like electron density and water vapor pressure vary with altitude. And the bottom image is from the Cosmic 1 mission, and it illustrates the same process. It has clearer labeling for better understanding. When we did an interview with Dr. Kate Thayer-Calder from NCAR, she stated that some satellites are equipped with multiple instruments so they can detect a wide range of atmospheric components simultaneously. An example she gave us is that LiDAR can detect cloud height and structure, but it can't penetrate through thick clouds. On the other hand, long-wave radar can see through clouds and gather data about what's inside, but it doesn't provide temperature information. And she said that this is especially valuable by combining these different instruments. It helps balance the strengths and limitations to build a more complete, accurate picture of the atmosphere. With data workflow, the Community Earth System Model is a powerful tool used to simulate Earth's climate system, and it's managed through a framework called CIME, which is short for Coupling Infrastructure for Modeling the Earth. This system allows for configuration of different models like the ocean, atmosphere, and the land. After configuration, they all communicate through a central coupler, which from what I've researched acts like a bridge between these individual models. And with the cyclic workflow engine, it manages a sequence of simulations by coordinating when each part of the system runs and how they exchange data. The MAPS workflow is designed to control the data simulation process, which combines these models with observations to create a refined analysis of the system. And this process involves a loop where a configured model is compared to new observations, and then the model state is updated to incorporate these new observations. And this iterative process helps to keep the model on track by continually refining its understanding of the system. To help mitigate this process, the workflow runs a high-performance computing system and uses shell scripts to automate these iterative steps. Once the modeling and processing steps are completed, the data may be stored and shared, which is where the Research Data Archive, or RDA, comes in. The RDA is a major platform providing long-term preservation and access where researchers can access large data sets and it uses Globus to support efficient and secure access by handling large-scale file transfers, which is facilitated by a specialized science DMZ network. This network is designed specifically for high-speed data movement in scientific environments to minimize latency, and it helps reduce bottlenecks and security risks since it's not part of the main campus's network. The images from NCAR CESM workflow documentation represents all the components integrated into CIME and how it manages the Community Earth System Model along with other science repositories. And one thing I found interesting is that NCAR actually has a partnership with Amazon S3 to make large datasets like the CESM2 available to a wider audience in the cloud, which allows researchers, including those outside of NCAR's high-performance commuting environment, to analyze the data from datasets.
Supercomputers are essential for running advanced scientific models that simulate the Earth system. These models often are written in Fortran, a language known for its efficiency and in numerical in scientific computing. One major model is the CESM, which we heard about earlier, which is the Community Earth Systems Model, and it's fully coupled with global climate models with around 5 million lines of code. The CESM simulates various Earth components like the atmosphere, oceans, glaciers to study past, present, and future climate scenarios. To support researchers working with outputs from models like the CESM, tools like GeoCat were developed. GeoCat is short for the Geoscience Community Analysis Toolkit. GeoCat provides scalable open source tools for data analysis and visualization using Python. GeoCat focuses on making Earth system science more accessible and user-friendly, even for large or unstructured data sets. Vapor, the visualization analysis problem for ocean, atmospheric, and solar researchers, is another powerful tool. It provides an interactive 3D visualization environment for creating both animations and still frame images. What makes Vapor especially powerful is its ability to handle very large data sets, even to a terascale level, on standard hardware. And thanks to VDC, Vapor's data collection model, it supports various scientific data formats, and includes built-in Python interpreter, enabling researchers to explore and manipulate data directly within the platform. And then finally, there's DART, the Data Simulation Research Testbed. DART has helped to improve model accuracy by integrating observational data and providing a rigorous framework that connects both modelers and observationalists. And over time, DART has grown into a key platform, not used just at NCAR, but throughout the geoscience community. And then when we were researching, we got to interview Dr. Kate Thayer-Cadler, who works at NCAR, and she explained how data produced by NCAR is used by a wide variety of people and organizations. One such user she mentioned was the IPCC, which is the Intergovernmental Panel on Climate Change, which relies heavily on NCAR's data to provide policymakers with scientific evidence that they need to create more informed climate policies. But the impact goes just beyond governments. Universities use this data for research and education, and scientists across the globe depend on it to study climate systems, weather patterns, and geospace. One of the key values NCAR emphasizes is making sure that the scientific results are reproducible, which is why it is so important for them to have data that is both accessible and transparent and very open to the public. The only time the data isn't immediately available is during an initial embargo period, right after it's collected and analyzed, so that it gives priority to the NCAR researchers to publish their findings and to make sure the data is correct and true. And most of the stored data is stored in the RDA, which Priscilla was able to talk about earlier.
Now moving on to the challenges. So NCAR doesn't just collect data in one location. They receive information from satellites, field stations, and atmospheric systems worldwide. This creates significant logistical hurdles, especially when real-time data is needed for critical weather forecasting. Also, the Derecho supercomputer generates massive model outputs that need to be distributed to researchers and government agencies quickly and securely. What makes data movement particularly challenging is that some data collection occurs in remote or harsh environments, like mountaintops or during severe storms, where connectivity is unreliable. So NCAR has had to develop specialized protocols and network infrastructure to ensure data integrity when transmitting data from these locations. Looking ahead, NCAR has ambitious plans to advance their capabilities. They're working on expanding their satellite observation network through the COSMIC program, which will dramatically increase the precision and coverage of atmospheric data collection worldwide. In parallel, their computational scientists are developing more sophisticated Earth system models that will operate at unprecedented resolutions, allowing for more accurate climate projections. These advancements require significant computing power, so NCAR is also planning major upgrades to their Derecho supercomputing infrastructure. Beyond the technical aspects, they're also focused on democratizing access to their research by creating more intuitive data portals and even launching citizen science initiatives that allow non-specialists to contribute to data collection efforts. These combined efforts reflect NCAR's commitment that are pushing the boundaries of understanding Earth's complex atmospheric systems. Yeah. Thank you.
I just want to take this time to again thank all the students. All your hard work this semester has been fantastic. And yeah, it was both groups did a fantastic job with their presentations. I also like to thank everyone for being here, everyone for taking the time to be here today. We're really excited to see all of the outside faces, and of course thanking the NSF as well for supporting us. We've really enjoyed this program. This is our going into our fourth year, and so we've just really enjoyed getting to know all the fellows, and we will be in touch for sure. Like we say, once a CICFer, always a CICFer. And we're very excited for the students that are going on to summer projects as well. But we'll also be in touch with other opportunities. So we're kind of constantly in touch with you. And there's an alumni network as well. So